Pluto, the perplexing bantam planet. Living at the external edges of our planetary system, Pluto is generating significant interest within the galactic community. Recent reports have suggested a potential encounter with Neptune, raising concerns among researchers and space enthusiasts alike. Prominent scientists, including Neil deGrasse Tyson and Michio Kaku, have raised alarms about the possible consequences of such a celestial conflict. But how did Pluto end up on a collision course with its distant neighbor, and what could such a cosmic impact mean for life on Earth? Let's explore this unfolding situation. Once considered a full-fledged planet, Pluto was later reclassified as a dwarf planet due to its peculiar orbit. Despite this redefinition, Pluto continues to captivate and intrigue astronomers. Recent predictions from well-known scientists emphasize a worrying proximity between Pluto's orbit and that of Neptune. These experts warn of a potential collision between the two bodies, which could pose a serious threat to Earth. Pluto's journey around the Sun is marked by its unique orbital characteristics. Its orbit takes an extraordinary 248 years to complete, and since its discovery in 1930, Pluto has yet to finish a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a stark contrast to the nearly circular orbits of the major planets. Moreover, Pluto's orbit is tilted at an angle of 17 degrees to the ecliptic plane, making its path steeper compared to other planets. One of the most striking features of Pluto's orbit is its intersection with Neptune's path. For about 20 years during each orbit, Pluto ventures closer to the Sun than Neptune, defying expectations based on their relative positions in the solar system. So, why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational influences exerted by other planets. The shape of Pluto's orbit presented a perplexing puzzle for astronomers shortly after its discovery. Unlike most planets whose orbits are relatively close to the ecliptic plane, Pluto's path is steeply inclined and highly elliptical. The discovery that Pluto's orbit crosses that of Neptune only deepened the mystery. Yet, despite these complexities, the stability of Pluto's orbit serves as evidence of the intricate space mechanics at play. The three-body problem in celestial mechanics helps explain the unpredictable movements and gravitational interactions between three celestial bodies, such as Pluto, Neptune, and the Sun. This phenomenon sheds light on the complex interactions of their orbits. Terms like azimuthal vibration, scope libration, and the VZK swing all contribute to understanding this celestial mystery. Astrophysicists argue that the south libration, a mechanism that helps maintain planetary orbits, plays a key role in the relationship between Pluto and Neptune. This concept suggests that when Pluto crosses Neptune's orbit, it is always positioned at least 90 degrees away from Neptune, thus preventing potential collisions. Scope libration ensures that when Pluto nears Neptune or other giant planets, it remains entirely above their orbital plane, further protecting it from catastrophic impacts. The VZK swing explains why Pluto's orbit, although appearing irregular, remains stable over time. Despite these stabilizing forces, Pluto's orbit is technically chaotic. Mathematical simulations from the late 1980s revealed that Pluto's path, though seemingly steady, can still exhibit small deviations that lead to significant differences over millions of years. However, these irregularities do not jeopardize Pluto's stability in the long term. Recent computer simulations have advanced our understanding of how massive planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun-Neptune's special resonance with Pluto. Completing 3 orbits for every 2 of Pluto contributes to the long-term stability of Pluto's path. Jupiter's massive gravity also plays a crucial role, and even Saturn's influence, though smaller, helps stabilize Pluto's orbit. Through extensive research, scientists have demonstrated that the combined gravitational forces of Neptune, Jupiter, and Saturn ensure Pluto's safe and steady evolution in space over billions of years. These peculiarities in Pluto's orbit are crucial for maintaining the order and stability of celestial mechanics within the solar system. Without such forces, the solar system could descend into greater chaos, potentially causing disastrous collisions or ejecting celestial bodies from their stable orbits, with far-reaching consequences for other planets. Understanding Pluto's orbit is particularly important as discussions emerge about a potential collision with Neptune in the future. This knowledge provides us with valuable insight into the dynamic nature of the planetary system. Pluto's case is a prime example of how orbits that seem unstable can reach equilibrium through complex gravitational interactions and orbital mechanics. Investigating the depths of space often reveals the unpredictable nature of celestial bodies. Pluto's orbit serves as a striking example of this unpredictability. The nature of orbital disorder highlights the delicate dependence of a celestial body's path on its initial conditions. Even slight variations in Pluto's position or speed can significantly alter its long-term trajectory. Programmatic simulations have been instrumental in helping researchers understand how Pluto moves through space. By making minor adjustments in these simulations, astronomers can observe how small changes can have profound effects on Pluto's path. These simulations have uncovered that, despite the stabilizing forces like south libration, Pluto's orbit can still show irregularities. A tiny deviation in Pluto's initial position or speed could lead to substantial changes in its long-term path. Yet, despite these inherent chaotic features, Pluto's orbit remains stable over time, suggesting an underlying order amidst its apparent whimsy. Predicting the future paths of celestial bodies, particularly those like Pluto with highly unusual orbits, is incredibly challenging. The inherent unpredictability of these systems makes long-term projections highly uncertain. Mathematical simulations help us understand and anticipate the future movements of celestial bodies, but they also reveal the limits of our predictive capabilities. These models rely on precise initial conditions and complex simulations, and even a small error can lead to vastly different outcomes. This chaotic nature of celestial orbits, such as Pluto's, serves as a reminder of the ever-changing universe. While we've made considerable progress in understanding space, Pluto's case illustrates how much more we have yet to learn. Understanding the gravitational effects of massive planets on Pluto's orbit offers significant insights into the broader dynamics of our planetary system. It shows how each planet's presence and position can influence the stability and trajectory of other bodies. Yet, despite these intricate forces, prominent astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. This raises the question, why is a collision, which seems unlikely given these complex dynamics, now a matter of growing concern? Neil deGrasse Tyson, a well-known astrophysicist, offers an intriguing perspective on the mysteries of our solar system, particularly in relation to Pluto. Tyson, famous for renaming Pluto as a dwarf planet, shares his insights into how our understanding of celestial mechanics is constantly evolving. He views Pluto's reclassification not as a downgrade, but as a necessary adjustment to our expanding knowledge of the diverse objects orbiting the Sun. Tyson's approach to celestial mechanics emphasizes ongoing learning and adaptation. He sees the complexities of orbits like Pluto's as indicative of how much more there is to discover in space. Tyson also understands how space-related events and discoveries, such as Pluto's renaming and its peculiar orbit, capture the public's imagination and spark interest in astronomy. Through examining the dynamic and sometimes irrational aspects of space mechanics, Tyson hopes to foster a deeper understanding and appreciation of the universe. Tyson has raised concerns that the three-body problem could eventually pose a real danger, suggesting that a collision with Neptune may be long overdue. He stresses that such an impact could disturb the balance of the solar system, potentially leading to devastating consequences that could even affect Earth. A collision between Pluto and Neptune would be a rare and catastrophic event in our planetary system. It could release a tremendous amount of energy, possibly destroying Pluto due to its smaller size and icy composition. Debris from the collision could scatter across the nearby planets, posing risks to other celestial bodies and their moons. For Neptune, the impact could alter its atmosphere and orbit, depending on the specifics of the event. Michio Kaku, a renowned theoretical physicist known for his work in string theory and science communication, offers a unique perspective on this situation. His views on the future of space exploration and the relationship between celestial mechanics and theoretical physics provide deep insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its orbit as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, he argues, can provide valuable insights for future space missions. This knowledge can assist in navigating the solar system more effectively, anticipating potential risks, and planning missions to the outer regions of our solar system and beyond. Kaku stresses that the lessons learned from studying Pluto's orbit can be applied to exploring other celestial bodies, providing a roadmap for understanding distant worlds. He often highlights the deep connection between celestial mechanics and theoretical physics. Kaku believes that the movements and interactions of planets, such as the gravitational pull between Pluto and Neptune, are not isolated events but are tied to fundamental principles of physics. His work in string theory seeks to unravel these principles at the most basic level. He proposes that studying the intricacies of celestial mechanics, such as Pluto's orbit, can yield insights into the fundamental laws of the universe. Like Tyson, Kaku has also addressed the potential collision between Pluto and Neptune, relating it to his theories about the universe. If the two were to collide, it would be a monumental event in astronomy, offering a unique observational opportunity that could contribute to our understanding of string theory. String theory, a theoretical framework that replaces point-like particles with one-dimensional strings, attempts to describe the fundamental forces and matter in the universe. A collision of such magnitude in the planetary system could create extreme conditions of energy and gravity, offering insights into the behavior of fundamental particles and forces under extraordinary circumstances, an area of significant focus in string theory. Moreover, the gravitational waves produced by such a collision could provide valuable data for testing predictions related to gravity and space-time. While the direct impact on Earth would be negligible due to our distance from the outer planetary system, the scientific implications of such an event could be immense. It could contribute to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a striking example of celestial mechanics, demonstrating both stability and chaos within our planetary system. The unique characteristics of its orbit, influenced by the gravitational forces of neighboring planets, especially Neptune, highlight the complex and dynamic nature of space. The universe holds countless mysteries, and the three-body problem is just one of them. There are other potential catastrophes that researchers continue to monitor. While the chances of planets colliding in space are low, it is not entirely impossible. The way planetary orbits are affected by gravitational interactions is explained by the three-body problem. In some star systems, like TRAPPIST-1, which contains 7 Earth-sized planets, the gravitational forces can create a rhythmic pattern called orbital resonances. Over time, these patterns may cause the planetary paths to become less stable, possibly leading to collisions. Although no collisions are currently occurring in systems like TRAPPIST-1, researchers closely monitor these systems to understand how planets influence each other's orbits. This knowledge helps us better grasp the movements of planets in space. Rogue planets, which are planets drifting through space without a star, introduce another level of unpredictability. These planets, once part of a star system, are ejected due to gravitational disturbances or other celestial events. Over time, they can travel vast distances and potentially encounter other star systems. If a rogue planet enters a nearby planetary system, there is a slight chance it could collide with a planet in that system. However, given the vast emptiness of space, the likelihood of such a collision is extremely low. The immensity of interstellar distances and the relative scarcity of planets in open space act as barriers to frequent collisions. Furthermore, rogue planets are relatively rare compared to the number of stars and planets in stable orbits, making such encounters even more unlikely. The impact of space exploration on our understanding of celestial events. The study of celestial bodies like Pluto is not only about understanding the objects themselves, but also about advancing our knowledge of the universe at large. The mysteries of space, whether it's Pluto's eccentric orbit, the potential risks it poses to Neptune, or the gravitational effects between distant planets, invite a broader understanding of cosmic mechanics. Such investigations help researchers refine theories about how planets interact with one another, how they move through space, and how various forces shape their orbits. But beyond the technical aspects of orbital dynamics, these studies also shed light on deeper philosophical questions about our place in the universe. As technology advances, so too does our ability to observe and analyze distant celestial objects. Telescopes and space probes that capture images of distant planets, moons, and even asteroids have provided an unprecedented level of detail about the solar system. By sending probes to the outer reaches of the solar system, scientists have gathered data that was once unimaginable. These missions have allowed us to peer closer at objects like Pluto, whose distant and irregular orbit was once purely speculative. With more powerful instruments, astronomers are continuously revising their models of the solar system structure, making space exploration a crucial tool in both answering and raising new questions about the cosmos. In particular, Pluto's reclassification from a planet to a dwarf planet has sparked discussions not only within the scientific community but also in the broader public. The debate over Pluto's planetary status highlights how science is an evolving process, where new discoveries can change the way we categorize and understand the universe. This process of continual revision challenges our perceptions and emphasizes the need for flexibility in scientific inquiry. The more we explore, the more we realize how much remains to be discovered, not just about Pluto and its interactions with Neptune, but about the nature of space itself. Pluto's case also serves as a reminder of the importance of interdisciplinary research. While astronomers focus on the physical dynamics of celestial bodies, theoretical physicists, like Tyson and Kaku, provide essential frameworks to interpret and explain these movements. The cross-pollination of ideas between these disciplines brings about new insights that help refine models of gravitational forces and the movement of celestial objects. String theory, for example, may provide a unified explanation for the forces at play in planetary motion, extending our understanding of the universe beyond the visible world.